continuation of work that started last year on extra thin S355 strip steel, microalloyed with vanadium. So I'll try to be as brief as possible due to the time constraints. So basically, just to remind you that there is a demand for extra thin or less than 2 millimeter thick, low carbon, high strength strip steel. In particular, the S355MH specification, that requires yield strength above 355, UTS between 450 and 570 MPa with satisfactory ductility, to be used in the light structural design or racking and shelving, and as well as the tubing industries. So as you all know, to achieve high strength in low carbon steels, we need something extra. And these days, last 40, 50 years, we've been using vanadium, niobium, titanium combinations for precipitation hardening and or enhanced grain refinement. So the specific objective on this work was to develop and compare the vanadium microalloyed steel, hot strip steel, performance against the conventional niobium titanium steels that we've historically used in terms of rollability, shape, consistent target thickness, and mechanical properties, of course. In thin material, in other words, we're talking particularly between, say, 1.4 and 1.9 millimeters, and to be produced on a conventional hot strip mill. So we started off using Bob Glodowski's empirical formula for yield strength that he collected over the years, which is shown over there, and it's proved to be fairly reliable, where you can predict yield strength as a function of simply manganese, vanadium, and total nitrogen content. So we were aiming for a yield strength of 385 MPa, which is 30 megapascals above the minimum spec. So this would typically give us, a typical composition as shown below. A low carbon, 0.9 manganese, slightly lower manganese than normal, and then 0.55 vanadium, and about 100 parts per million nitrogen, keeping the aluminium low, for reasons that have been discussed in previous PPP meetings. So our scope was as follows. It's fairly simple. So you could reach the hot strip mill on top over there, where we chose a finishing temperature of 840 degrees, varied the coil temperature between 575 and 625, and final gauge length between 1.5 and 2.5. We initially started with thicker material and then worked our way down, keeping the reheat temperature constant to 1200 and aiming for a final width of, between 1220 and 1260 millimeters. The mechanical properties, of course, were evaluated. UTS, yield strength, UTS, elongation, end value, and thickness, and an optical microscopy and hardness. And then we also looked a bit at the rolling force and the mean flow stresses to make an assessment on shape. So this is results that we've obtained so far, a selection of results. What we see here is obtaining the mean flow stress and force behavior was assessed using mill logs, and the Ford and Alexander roll force equation are shown top right over here, where the force is a function, of course, of width, contact length, Z, the mean, the arithmetic mean in terms of reduction, and then the stress. Z and L and contact length are given by those two equations there, which are functions of the roll radius and the draft. And you can see here, I have plots of 1,5, 1,6 millimeter, 1,9, 2,5 millimeter, and I'm comparing vanadium against niobium titanium over here. You will see, if you just scan left to right, how the mean flow stress, was the top graphs, are comparable in both grades, and the plots below it are the strain rates that were applied during each finishing stage. So the roll forces per unit width were also pretty comparable. But now what is interesting here is that they were comparable despite the fact that the rolling temperature of the vanadium steels were comfortably below that of the niobium titanium. And this is also for a constant rolling schedule in the finishing train. And also, the other exciting thing was that we could roll the vanadium steels wider. Here we have 1220, 1250 millimeter wide material, as opposed to the niobium titanium steel on the ultra thin, in other words, below 2 millimeters. It was only we only sort of comfortable up to 1,000 millimeters wide. So that was a major plus. The initial, one of the objectives was to be able to alternate between niobium and titanium, given that the price of the day. But here we are able to roll wider material as well without challenging the roll force on the actual mill. Just looking at some microstructures, this was a 2.5 millimeter, comparing the niobium titanium grade against the vanadium nitrogen grade. As we know, there's more grain refinement that occurs during the thermomechanical rolling of vanadium steel, hence the finer grain. We all know that. But the actual strength most of the strength comes from the precipitation strengthening after rolling. This is what the microstructure looks typically like across the width of vanadium, a thin, 1.5 millimeter thick strip. You'll notice a very fine grain towards the edge in the region of about 3 microns. It's transformed from fully recrystallized austenite. Then towards the quarter width and the mid width, we have grain size in the region of 6.5 microns. So what we did was, initially we did a 150-ton trial. That's just a handful of coils. But then after the success of the 2.5 millimeter material, we decided we went thinner, and we did a 1,000-ton trial, plus minus 60 coils. And here we have some tensile results for you. This being the red lines being the max or min of that S355MH spec I was telling you about. You can see that RD standing rolling direction, TD transverse direction. You can see that the yield strengths in both directions are fairly similar and fairly isotropic. However, what we're seeing here, so that's for 575 Celsius. But as you increase the core temperature, there's a distinct drop in strength. So that was a fairly significant finding, probably related to size distribution of vanadium nitride, carbon nitride. As with many other steels, UTS fairly constant across the board. And then as far as the A565 elongation is concerned, comfortably above the minimum spec, although the elongation was comfortably higher in the rolling direction. So in conclusion, our findings to date are as follows. So for extra thin, with less than 2 millimeter hot rolled vanadium nitrogen strip, the S355MH spec is comfortably achieved for strip wider than 1,200 millimeters. For the niobium steel, we could only, if we go beyond 1,000 millimeters, we start running into instability problems. As we would like to report in more detail later towards September with the next PP meeting. And then if we want to go to a tougher material, it won't be now for strip, but if you needed to go to an S355JR, you would unfortunately need to increase the manganese or the vanadium and nitrogen, as per that equation that I showed you, in order to get the minimum UTS up to above 510 MPa. That was an original goal, but we found that we weren't going to quite make this big, so we had to go down back to the S355MH. And then coil temperature definitely has an influence on yield strength, but only has a very moderate effect on UTS and elongation. Dropping the coil temperature from 625 down to 575 increased yield by 25 MPa. We have found also fairly isotropic strength properties, transverse versus longitudinal, which was probably a good thing. And then for the rolling parameters we employed or currently employing, strip edges have a very fine polygonal ferrite structure, which was transformed from crystallized austenite. The outstanding work going forward now is to monitor. We are now going full production now, monitoring full-scale production, extra thin, microalloyed S355 strip for about 6 months. After sufficient data have been accumulated, we're going to compare, of course, properties, but also shape defects.
I'll check in the proposal. I'll just finish.
To be honest, we did detect a few pinches defects in this very thin steel, but not more frequent than that has been experienced in niobium steels that were processed earlier. We'll also look for isotropy of the vanadium nitrogen steel as well, and of course all this will be compared with niobium production. And then of course a report and a paper, hopefully a paper. And this is just our Gantt chart. So everything in green has basically been completed. What remains here, as I said, is full scale. We'll be monitoring full scale production from about now to the end of the year. But for evaluation will sort of terminate by the end of August. And hopefully we'll have a final report for you come October. Thanks. That's it.
Okay, thank you very much, Kevin. I think again we're making some good progress there. Are there any questions or comments on Kevin's presentation?
Can I make a comment just for correction on the grain sizes on the 1.5 millimeter? Kevin did mention between 6 and 7 micrometers, but the actual grain size there is about 4.5 micrometers. That's on the 1.5 millimeter at the quarter width as well as the next slide. Yeah.
Yes.
Yeah. It's about 4.5.
In the bulk.
Yeah.
Yeah. And here it's about 3.
Yeah. It's, yeah. That was verified.
Yeah. Okay.
A very quick question from me once again. Kevin, you were showing the test results, right?
Yes.
In the box plot. There, in the 625 degrees CT, RD versus TD, the variation seems to be significantly narrower in RD. Is that something, some physical phenomenon happening, or is it just because the less number of tests conducted?
Yeah. The
variation is very, very narrow, right? Particularly
in
very
narrow.
2.5 mm.
Yeah. I can't explain that. It's probably just due to the amount of tests that we've tested up to now, and it haven't been a lot. As I said, it's 60 spread over a number of conditions.
Another thing, the plant results mostly when they from the volume direction.
No, this is all Emery.
Oh, this is all tested by.
Oh no, sorry. No, this is plant.
Oh, plant.
Yeah, I think in 6 months' time, I'll have a lot more coils to show you, and you probably find them come a bit wider.
Okay, right.
Thank you. Yes.
Right, thanks.
Yeah, Kevin, just while you've got that plot up, the results from the vanadium steel look quite isotropic, comparing RD and TD. Did you say you'd got similar results for the niobium steel, or were you going to get them? Because my guess would be niobium would be worse.
Or it would be worse, and I think there's probably a good reason for that. It's because, you know, I think it's because, you know, the size of the niobium atom is much bigger than iron, and whereas vanadium is more similar to iron, you know. So you could argue the way that the material is flowing will be more in unity with vanadium will be more sort of flowing with iron than niobium would. But I've got niobium data that I haven't shown yet, and it is definitely more isotropic, the vanadium steel.
Also, something that we saw with the niobium microstructures, the grains are more elongated compared to the vanadium grade.
Yeah, my guess is going to be that we're going to get more deformation of the austenite grains in the niobium situation, and maybe we get some more texture or something for the niobium steel.
Yes. I think that would make a good study, Dave, going forward. We're not sure about the funding of these projects going forward, but that indeed would make a good study, just the isotropy, niobium versus vanadium, you know, for similar strength grades. Yeah.
Okay, well, thanks for that, Kevin. Again, I'm sorry to cut things slightly short, but in the interest of time, we'd better move on to our next and final presentation. So thanks for that, Kevin. If you could click off your screen, please. Our next presentation is from Texas A&M University, and this is a new proposal, a new project proposal for us. So Sarvajit,